Start of Slide 1. Slide Caption. Chapter 12. Contactors and Magnetic Motor Starters. Section 12-1. Manual Switching. Section 12-2. Manual Contactors. Section 12-3. Manual Starters. Section 12-4. Magnetic Contactors. Section 12-5. Magnetic Motor Starters. Section 12-6. Contactor and Magnetic Motor Starter. Section 12-7. Troubleshooting Contactors and Motor Starters. End of Slide 1. Start of Slide 2. Slide Caption. Objective. Section 12-1. Manual Switching. By the end of this PowerPoint, you should be able to explain why knife switches were discontinued as a means of controlling motors and how they were improved. End of Slide 2. Start of Slide 3. Slide Caption. Knife switches were the first devices used to start and stop electric motors. See Figure 12-1. In the late 1800s, when electric motors were introduced, a method had to be found to start and stop them. This was accomplished through using knife switches. Knife switches were eventually discontinued as a means of controlling motors for three basic reasons. First, the open knife switch had exposed live parts that presented an extreme electrical hazard. In addition, any applications where dirt or moisture were present made the open switch vulnerable to problems. Second, the speed of opening and closing contacts was determined by the operator. Considerable arcing and pitting of the contacts led to rapid wear if the operator did not open or close the switch quickly. Finally, most knife switches were made of soft copper, which required replacement after repeated arcing, heat generation, and mechanical fatigue. End of Slide 3. Start of Slide 4. Slide Caption. A knife switch is enclosed in a steel housing, has an insulated external handle, and includes an operating spring for improved operation and safety. See Figure 12-2. As industry demanded more electric motors, improvements were made to knife switches to make them more acceptable as control devices. First, the knife switch was enclosed in a steel housing to protect the switch from external forces and from emitting sparks. An insulated external handle was added to protect the operator. Also, an operating spring was attached to the handle to ensure quick opening and closing of the knife blade. The switch handle was designed so that once the handle was moved a certain distance, the tension on the spring forced the contacts to open or close at the same continuous speed each time it was operated. End of Slide 4. Start of Slide 5. Slide Caption. 12-1 Checkpoint. Why is it important to open, break, an electrical circuit as fast as possible? Despite being eliminated for direct control of motors, knife switch operation is still used in what type of electrical equipment? End of Slide 5.
Start of Slide 6. Slide Caption. Objectives. Section 12-2. Manual Contactors. By the end of this presentation, you should be able to define manual contactor and explain why one should not be used as a motor starter. Describe double break contacts and explain how they are used. Describe how to draw a wiring diagram for manual contactors. End of Slide 6. Start of Slide 7. Slide Caption. A manual contactor uses push buttons to energize or de-energize the load connected to it. See Figure 12-3. A manual contactor manually opens and closes contacts in an electrical circuit. Manual contactors cannot be used to start and stop motors because they are missing overload protection that should be built into them for starting motors. Manual contactors are normally used with lighting circuits and resistive loads such as heaters or large lamp loads. A fuse or circuit breaker is normally included in the same enclosure with a manual contactor. End of Slide 7. Start of Slide 8. Slide Caption. Double break contacts break an electrical circuit in two places. See Figure 12-4. Double break contacts can act as a direct controller. Double break contacts are used in momentary push buttons. End of Slide 8. Start of Slide 9. Slide Caption. A three-phase manual contactor has three sets of normally open double break contacts. See Figure 12-5. One set of normally open double break contacts is used to open and close each phase in the circuit. The movable contacts are located on an insulated T-frame and are provided with springs to soften their impact. The T-frame is activated by a push-button mechanism. Similar to a disconnect, the mechanical linkage consistently and quickly makes or breaks the circuits. End of slide 9. Start of slide 10. Slide caption: the oxide, rust, that forms on silver alloy contacts is an excellent conductor of electricity. See figure 12-6. In the past, a major problem with knife switches was that they were constructed from soft copper. Today, most contacts are made of a low-resistance silver alloy. Silver is a mixed alloy of cadmium or cadmium oxide to make an arc-resistant material that has good conductivity with a low resistance. In addition, the silver alloy has good mechanical strength, enabling it to endure the continual wear encountered by many openings and closings. Another advantage of silver alloy contacts is that the oxide, rust, that forms on the metal is an excellent conductor of electricity. Even when the contacts appear dull or tarnished, they are still capable of operating normally. End of slide 10.
Start of slide 11. Slide caption: a wiring diagram shows the connection of an installation or its component devices or parts. See figure 12-7. Manual contactors directly control power circuits. Power circuit wiring is shown on a wiring diagram. An understanding of wiring diagrams is required because an electrician may be required to make changes in power circuits as well as in control circuits. End of slide 11. Start of slide 12. Slide caption: in the wiring diagram for a dual-element heater with pilot lights, the low-heat heating element is operated when the low contacts in L1 and L2 are closed so that a connection is made to the low and common terminals of the heater. See figure 12-8. Wiring diagrams may be complex. For example, this wiring diagram for a dual-element heater with pilot lights contains various circuit paths. In this circuit, the low-heat heating element is operated when the low contacts in L1 and L2 are closed so that a connection is made to the low and common terminals of the heater. This allows the low-heat heating element to be energized. End of slide 12. Start of slide 13. Slide caption: in the wiring diagram for a dual-element heater with pilot lights, the high-heat heating element is operated when the high contacts in L1 and L2 are closed so that a connection is made to the high and common terminals of the heater. See figure 12-9. To operate the high-heat heating element, the high contacts in L1 and L2 are closed so that a connection is made to the high and common terminals of the heater. This allows the high-heat heating element to be energized. A low-heat pilot light and high-heat pilot light turn on to indicate each condition because each pilot light is in parallel with the appropriate heating element. End of slide 13. Start of slide 14. Slide caption: 12-2 checkpoint. Why are manual contactors not used to control motors? What is the advantage of using double break contacts instead of single break contacts? Why are silver alloy contacts better than copper contacts? Why are mechanical interlocks included on dual-element heating contactors? End of slide 14. Start of slide 15. Slide caption: objectives. Section 12-3. Manual starters. Explain the difference between a manual starter and a manual contactor. Explain the difference between how a fuse or circuit breaker protects a circuit and how overload relays protect running motors. Explain how overload heater coils operate to automatically turn off an overloaded motor. Describe how to select the proper AC manual starter. End of slide 15.
Start of slide 16. Slide caption: a manual starter is a contactor with an added overload protective device. See figure 12-10. Manual starters are used only in electrical motor circuits. The primary difference between a manual contactor and a manual starter is the addition of an overload protective device. End of slide 16. Start of slide 17. Slide caption: the three stages a motor goes through during normal operation include resting, starting, and operating under load. See figure 12-11. A motor at rest requires no current because the circuit is open. A motor that is starting draws a tremendous inrush current that is normally 6 to 8 times the running current when the circuit is closed. Fuses or circuit breakers must have a sufficiently high ampere rating to prevent the immediate opening of the circuit caused by the large inrush current required for a motor when starting. End of slide 17. Start of slide 18. Slide caption: an overload relay is required that does not open a circuit while a motor is starting but opens the circuit if the motor gets overloaded and the fuses do not blow. See Figure 12-12. Fuses or circuit breakers must protect the circuit against the very high current of a short circuit or a ground fault when the fuses do no blow open to protect the motor. End of slide 18. Start of slide 19. Slide caption: a heater coil is a sensing device used to monitor the heat generated by excessive current and the heat created through ambient temperature rise. See Figure 12-13. Many different types of motor overload heater coils are available. The operating principle of each is the same. A heater coil converts the excess current drawn by a motor into heat, which is used to determine whether the motor is in danger. End of slide 19. Start of slide 20. Slide caption: most manufacturers use a ratchet wheel and eutectic solder alloy combination to activate a trip mechanism when an overload occurs. See Figure 12-14. The eutectic alloy tube consists of an outer tube and an inner shaft connected to a ratchet wheel. The ratchet wheel is held firmly in the tube by the solid eutectic alloy. The inner shaft and ratchet wheel are locked into position by a Paul locking mechanism, so that the wheel cannot turn when the alloy is cool and solid. Excessive current applied to the heater coil melts the eutectic alloy. This allows the ratchet wheel to turn freely on the eutectic alloy fluid. End of slide 20.
Start of slide 21. Slide caption: in a manual starter overload relay, the compressed spring tries to push the normally closed contacts open under normal operating conditions. See Figure 12-15. The main device in an overload relay is the eutectic alloy tube. The compressed spring tries to push the normally closed overload contacts open when motor current conditions are normal. The Paul is caught in the ratchet wheel and does not let the spring push up to open the contacts. End of slide 21. Start of slide 22. Slide caption: the overload relay is reset by pressing the reset button, which forces the Paul across the ratchet wheel until the contacts are closed and the spring and ratchet wheel are returned to their original condition. See Figure 12-16. The cause of an overload must be found before resetting an overload relay. A relay trips on resetting if the overload is not removed. Once the overload is removed, the device can be reset, only requiring time for the solder eutectic to solidify again. The reset button is pushed, which forces the Paul across the ratchet wheel until the contacts are closed and the spring and ratchet wheel are returned to their original condition. The start push button can then be pressed to start the motor. End of slide 22. Start of slide 23. Slide caption: AC manual starters are selected based on phasing, number of poles, voltage, starter size, and enclosure type. See Figure 12-17. Also see Appendix. Electricians are often required to select AC manual starters for new installations or replace ones that have been severely damaged due to an electrical fire or explosion. In either case, the electrician must specify certain characteristics of the starter to obtain the proper replacement. AC manual starters are selected based on phasing, number of poles, voltage, starter size, and enclosure type. Starter sizes are given in General Motor Protection Tables. General Motor Protection Tables indicate motor protective device sizes based on motor horsepower, current, fuse classification, and wire size. End of slide 23. Start of slide 24. Slide caption: AC manual contactors can be divided into single-phase and three-phase contactor types. See Figure 12-18. On single-phase systems, there are two hot wires and one neutral wire that is connected to ground at the service panel. A 120-volt, one-phase power source has one hot wire, the ungrounded conductor, and one neutral wire, the grounded conductor. A 230-volt, single-phase power source has two hot wires, L1 and L2, where both are hot and ungrounded conductors with no neutral. A three-phase power source has three hot wires, L1, L2, and L3, and no neutral. End of slide 24. Start of slide 25. Slide caption. Manual motor starters are used in applications such as conveyor systems and drill presses. See Figure 12-19. In most applications, the manual starter provides the means of turning on and off the device while providing motor overload protection. End of slide 25.
Start of slide 26. Slide caption, 12-3 checkpoint. What is the primary difference between a manual contactor and a manual starter? When does a motor controlled by a motor starter draw the highest amount of current? If a fuse or circuit breaker directly opens a circuit when the current limit is reached, do overload heaters open and break the circuit when their current limit is reached? 4. When an overload device trips, does it have to be replaced like a fuse? 5. In a single-phase motor starter, does the starter have to open both the ungrounded hot conductor and the neutral conductor? 6. Do all ungrounded hot conductors have to be opened when controlling loads? End of slide 26. Start of slide 27. Slide caption, Objectives. Section 12-4. Magnetic contactors. By the end of this presentation, you should be able to describe magnetic contactors and explain how they are used. Explain how to design a two-wire control circuit that can be used to control a magnetic contactor. Explain how to design a three-wire control circuit that can be used to control a magnetic contactor. Explain why opening a DC circuit causes more of an arc contact problem than when opening an AC circuit. Define arc chute and explain its usage. Explain how DC magnetic blowout coils work. Explain how to choose a magnetic contactor. End of slide 27. Start of slide 28. Slide caption, Contactors are used to make and break the electrical power circuit to lights, heaters, transformers, and capacitors. See Figure 12-20. Contactors may be operated manually or magnetically. Contactors are devices for repeatedly establishing and interrupting an electrical power circuit. End of slide 28. Start of slide 29. Slide caption, Solenoid action is the principal operating mechanism for magnetic contactors. See Figure 12-21. The linear action of a solenoid is used to open and close sets of contacts instead of pushing and pulling levers and valves. The use of solenoid action rather than manual input is an advantage of a magnetic contactor over a manual contactor. Remote control and automation, which are impossible with manual contactors, can be designed into a system using magnetic contactors. End of slide 29. Start of slide 30. Slide caption, in two-wire control, two wires lead from the control device to the contactor or starter. See Figure 12-22. The control device could be a thermostat, float switch, or other contact device. When the contacts of the control device close, they complete the coil circuit of the contactor, causing it to energize. This connects the load to the line through the power contacts. The contactor coil is de-energized when the contacts of the control device open. This de-energizes coil C, which opens the contacts that control the load. The contactor functions automatically in response to the condition of the control device without the attention of an operator. End of slide 30.
Start of slide 31. Slide caption, in three-wire control, three wires lead from the control device to the starter or contactor. See Figure 12-23. The circuit uses a momentary contact off push button normally closed wired in series with a momentary contact on push button normally on wired in parallel to a set of contacts that form a holding circuit interlock or memory. End of slide 31. Start of slide 32. Slide caption, a step-down control transformer is used to step down the voltage to the level required in the control circuit. See Figure 12-24. In most circuits in which the load is rated higher than 115 volts, normally 208 volts, 230 volts, 240 volts, 460 volts, and 480 volts. The control circuit is operated at a lower voltage level than the load. Normally, the secondary of the transformer is rated for 12 volts, 24 volts, or 120 volts. The voltage of a control circuit can be any voltage, AC or DC, but it is commonly less than 120 volts. 24 volts DC is one such industry favorite that is used for motor controller circuits. End of slide 32. Start of slide 33. Slide caption. Contactors have either an AC coil or a DC coil, and they may have either AC or DC contacts. See Figure 12-25. AC contactor assemblies may have several sets of contacts. DC contactor assemblies typically have only one set of contacts. In three-phase AC contactors, all three power lines must be broken. This creates the need for several sets of contacts. For multiple contact control, a T-bar assembly allows several sets of contacts to be activated simultaneously. In a DC contactor, it is necessary to break only one power line. End of slide 33. Start of slide 34. Slide caption. An electrical arc is created between contacts as they are opened. Prolonged arcing may result in damage to contact surfaces. See Figure 12-26. A short time period, often just a few thousandths of a second, exists when a set of contacts is opened under load. During this time, the contacts are neither fully in touch with each other nor completely separated. End of slide 34. Start of slide 35. Slide caption. The maximum arcing current is reached only once during any half cycle of AC voltage. See Figure 12-27. An AC arc is self-extinguishing when a set of contacts is opened. In contrast to a DC supply of constant voltage, an AC supply has a voltage that reverses its polarity 120 times a second when operated at a line frequency of 60 Hz, where Hertz is abbreviated as capital H and lowercase z period. The alternation allows the arc to have a maximum duration of no more than a half cycle. During any half cycle, the maximum arcing current is reached only once in that half cycle. End of slide 35.
Start of slide 36. Slide caption. Arc chutes and arc traps are used to confine, divide, and extinguish arcs drawn between contacts opened under load. See Figure 12-28. An arc chute is a device that confines, divides, and extinguishes arcs drawn between contacts opened under load. Arc chutes are used to contain large arcs and the ionized gases created by them. Arc chutes employ the d-ion principle, which confines, divides, and extinguishes the arc for each set of contacts. End of slide 36. Start of slide 37. Slide caption. The direction of the magnetic field around the conductor is determined by wrapping the right hand for electron current, or left hand for conventional current, around the conductor. The electron flow, right-hand motor rule indicates the motion of an arc cutting through magnetic lines of force. See Figure 12-29. A magnetic field is created around the current flow whenever a current flows through a conductive medium, in this case ionized air. When the thumb on the right hand points in the direction of conventional current flow, the wrapping fingers point in the direction of the resulting magnetic field. When the thumb on the left hand points in the direction of electron current flow, the wrapping fingers point in the direction of the resulting magnetic field. End of slide 37. Start of slide 38. Slide caption. Electromagnetic blowout coils rapidly extinguish DC arcs. See Figure 12-30. The electron flow motor rule states that when a current-carrying conductor, represented by the middle finger, is placed in a parallel magnetic field, represented by the index finger, the resulting force or movement is in the direction of the thumb. This action occurs because the magnetic field around the current flow opposes the parallel magnetic field above the current flow. This makes the magnetic field above the current flow weaker, while aiding the magnetic field below the current flow, making the magnetic field stronger. The net result is an upward push that quickly elongates the arc current so that it breaks or blows out. An electromagnetic blowout coil is often referred to as a puffer because of its apparent blowout ability. Actually, it just elongates the ion pathway until it becomes so long that there is not enough voltage to sustain the arc. End of slide 38. Start of slide 39. Slide caption: tables indicate the number/size designations and establish the current load carried by each contact in a contactor. See Figure 12-31. Magnetic contactors, like manual contactors, are rated according to the size and type of load by the National Electrical Manufacturers Association, known as NEMA. Tables are used to indicate the number/size designations and establish the current load carried by each contact in a contactor. The rating is for each contact individually, not for the entire contactor. For example, a size 0, 3-pole contactor rated at 18 amps is capable of, and rated for, switching 3 separate 18 amps loads simultaneously. End of slide 39. Start of slide 40. Slide caption: contactor dimensions vary from inches to several feet in length. See Figure 12-32. Contactors are selected based on type, size, and voltage available. End of slide 40.
Start of slide 41. Slide caption: 12-4 checkpoint. What happens to a load that was energized when a 2-wire control device is used and power is lost and then reapplied? What happens to a load that was energized when a 3-wire control device is used and power is lost and then reapplied? Does opening an AC or DC circuit cause the most problems in arc suppression? What happens to electrical contacts if their resistance increases? Why are arc chutes used? As conductor size numbers increase from AWG12 to 14, they can carry less current and power. What happens as a NEMA contactor size number increases from size 1 to size 2? End of slide 41. Start of slide 42. Slide caption: objectives. Section 12-5. Magnetic motor starters. By the end of this PowerPoint, you should be able to define magnetic motor starters and describe their different means of overload protection. Describe the characteristics that must be considered when selecting an overload heater. Explain how to select the correct overload heater for a given motor using a manufacturer selection chart. Define inherent motor protector and describe the different types. Explain how to troubleshoot circuit breakers. End of slide 42. Start of slide 43. Slide caption: a magnetic motor starter is a contactor that includes overload protection. See Figure 12-33. A magnetic motor starter is any electrically operated switching contactor that also provides some sort of motor overload protection. Magnetic motor starters include overload relays that detect excessive current passing through a motor and are used to switch all types and sizes of motors. Magnetic motor starters are available in sizes that can switch loads of a few amperes to several hundred amperes. End of slide 43. Start of slide 44. Slide caption: magnetic overload relays use a current coil that, at a specific overcurrent value, acts like a solenoid and causes a set of normally closed contacts to open to shut power off to the motor. See Figure 12-34. Magnetic overload relays provide another means of monitoring the amount of current drawn by a motor. A magnetic overload relay operates through using a current coil. At a specified overcurrent value, the current coil acts as a solenoid, causing a set of normally closed contacts to open. This causes the circuit to disconnect the motor power to protect it from damage. End of slide 44. Start of slide 45. Slide caption: the warping effect of a bimetallic strip is used as a means for separating contacts. See Figure 12-35. In certain applications such as walk-and-meet coolers, remote pumping stations, and some chemical process equipment, overload relays that reset automatically to keep the unit operating up to the last possible moment may be required. A bimetallic overload relay is an overload relay that resets automatically. Bimetallic overload relays operate on the principle of the bimetallic strip. A bimetallic strip is made of two pieces of dissimilar metal that are permanently joined by lamination. Heating the bimetallic strip causes it to warp because the dissimilar metals expand and contract at different rates. The resulting bend of the strip is used to actuate a set of switching contacts that indirectly disconnect power to the motor to protect it. End of slide 45.
Start of slide 46. Slide caption: trip indicators indicate that an overload has taken place within the device. See figure 12-36. Many overload devices have a trip indicator built into the unit to indicate to the operator that an overload has taken place within the device. A red metal indicator appears in a window located above the reset button when the overload relay has tripped. The red indicator informs the operator or electrician why the unit is not operating and that it is potentially capable of restarting with an automatic reset. End of slide 46. Start of slide 47. Slide caption: standard overload relays may be used on very large starters by using current transformers with specific reduction ratios. See figure 12-37. Large horsepower motors have currents that exceed the values of standard overload relays. To make the overload relays larger would greatly increase their physical size, which would create a space problem in relation to the magnetic motor starter. To prevent such a conflict, current transformers are used to reduce the current in a fixed ratio. A current transformer is used to change the amount of current flowing to a motor but reduces the current to a lower value for the overload relay. For example, if 50 amps were flowing to a motor, only 5 amps would flow to the overload relay through using the current transformer. Standard current transformers are normally rated in primary and secondary rated current such as 50/5 or 100/5. End of slide 47. Start of slide 48. Slide caption: the nameplate of a magnetic motor starter includes the class, type, and size of the starter. See figure 12-38. Overload heater coils for continuous duty motors are selected from manufacturer tables based on the motor nameplate full load current for maximum motor protection and compliance with section 430.32 of the NEC. The class, type, and size information of a magnetic motor starter are found on the nameplate on the face of the starter. The phase, service factor, and full load current of the motor are determined from the motor nameplate. Common applications use 40 degrees Celsius as the ambient temperature. Questionable ambient temperatures should be measured at the job site or determined by some other method. End of slide 48. Start of slide 49. Slide caption: manufacturer instructions on thermal overload relay selection detail restrictions that are placed on classes of starters. See figure 12-39. It is important to always refer to the manufacturer instructions on thermal overload relay selection to see if any restrictions are placed on the class of starter required. For example, unless a Class 8198 starter is used, motors with service factors of 1.15 to 1.25 may use 100% of the motor full load current for thermal overload selection. End of slide 49. Start of slide 50. Slide caption: manufacturers provide charts to use for selecting proper overload heaters. See figure 12-40. The correct heater selection chart must be used for the appropriate size starter. This information is also found within the enclosure of many motor starters. Each motor starter manufacturer has a chart that applies to their specific brand. End of slide 50.
Start of slide 51. Slide caption: special overload heater selection tables provide multipliers to compensate for ambient temperatures above or below the standard temperature of 40 degrees Celsius. See figure 12-41. As ambient temperature increases, less current is needed to trip overload devices. As ambient temperature decreases, more current is needed to trip overload devices. Most heater manufacturers provide special overload heater selection tables that provide multipliers to compensate for temperature changes above or below the standard temperature of 40 degrees Celsius. The multipliers ensure that the increase or decrease in temperature does not affect the proper protection provided by the overload relay. End of slide 51. Start of slide 52. Slide caption: most manufacturers provide charts for approximating full load current when motor nameplate information is not available. See figure 12-42. In rare instances, such as older installations or severely damaged equipment, it may be impossible to determine a motor full load current from its nameplate. Charts listing approximate full load currents based on average motor full load currents are available from most manufacturers when nameplates do not provide this information. End of slide 52. Start of slide 53. Slide caption: a magnetic motor starter can be used to control a pump motor. See figure 12-43. When using a magnetic motor starter to control a motor, the starter is wired following a standard line diagram. For example, a pump motor is controlled by a magnetic motor starter that uses a control circuit. The control circuit includes a 3-position selector switch with the 3 positions marked hand, off, and auto, along with a liquid level switch to control the motor starter. When the selector switch is placed in the hand position, the motor is on. When the selector switch is placed in the auto position, the motor is on only when the liquid level switch contacts are closed, meaning that the liquid is at or above the switch level. In the off position, the motor is off regardless of the position of the liquid level switch contacts. End of slide 53. Start of slide 54. Slide caption: bimetallic thermodiscs are normally used on small horsepower motors to directly disconnect the motor from the power circuit. See figure 12-44. A bimetallic thermodisc operates on the same principle as a bimetallic strip. The differences between these devices are the shapes of the devices and their locations. A thermodisc has the shape of a miniature dinner plate and is located within the frame of a motor. A bimetallic thermodisc warps and opens the circuit when a motor is overloaded. Bimetallic thermodiscs may be tied into the control circuit of a magnetic contactor coil where they can be used as indirect control devices. End of slide 54. Start of slide 55. Slide caption: a thermistor overload device combines a thermistor, solid-state relay, and contactor into a custom-built overload protector. See figure 12-45. A thermistor-based overload is a sophisticated form of inherent motor protection. A thermistor overload device combines a thermistor, solid-state relay, and contactor into a custom-built overload protector. End of slide 55.
Start of slide 56. Slide caption: circuit breakers, CBs, perform the same function as fuses and are tested in the same manner. See figure 12-46. A circuit breaker known as CB is an overcurrent protective device with a mechanism that automatically opens the circuit when an overload condition or short circuit occurs. CBs are connected in series with the circuit and operate much like a relay. They protect a circuit from overcurrents or short circuits. CBs are magnetically operated and are reset after an overload. A DMM is set to measure voltage is used to test CBs. CBs perform the same function as fuses and are tested the same way. See complete procedural list on page 264. End of slide 56. Start of slide 57. Slide caption: 12-5 checkpoint. Is the current rating listed on a motor nameplate the full load current known as FLC rating, the starting current rating, or the no-load rating? If a motor has an 8 amp FLC rating and a service factor of 1.25, how much current is the motor designed to handle for short periods of time? Will an increase in the ambient temperature increase or decrease the amount of current required to trip overloads? How are inherent motor protective devices reset once they are tripped? End of slide 57. Start of slide 58. Slide caption: objective. Section 12-6. Contactor and magnetic motor starter modifications. By the end of this PowerPoint, you should be able to explain what devices may be added to basic contactors or magnetic motor starters. End of slide 58. Start of slide 59. Slide caption: the devices that may be added to basic contactors or magnetic motor starters to expand their capability include additional electrical contacts, power poles, pneumatic timers, transient suppression modules, and control circuit fuse holders. See figure 12-47 for examples. Start of slide 60. Slide caption: 12-6 checkpoint. Is a transient suppression module used to help reduce transient voltages in the control circuit or motor power circuit? Is the time delay adjustable when a pneumatic timer is added to a motor starter? End of slide 60.
Start of slide 61. Slide caption. Objective. Section 12-7. Troubleshooting contactors and motor starters. State the procedure for troubleshooting a motor starter. End of slide 61. Start of slide 62. Slide caption. The contactor or motor starter is the first device checked when troubleshooting a circuit that does not work or has a problem. See Figure 12-48. The power circuit and the control circuit are checked if the control circuit does not correctly operate a motor. The two circuits are dependent on each other, but are considered two separate circuits because they are normally at different voltage levels and always at different current levels. See complete procedural list on page 267. End of slide 62. Start of slide 63. Slide caption. A troubleshooting guide used when troubleshooting contactors and motor starters states a problem, its possible cause or causes, and corrective actions that may be taken. See Figure 12-49. Manufacturers know best when it comes to troubleshooting their equipment. They will give you the best advice in the form of a troubleshooting guide. It will allow you to select from a list what type of trouble you are having and then suggest a cause or causes, along with corrective actions you should take to resolve the issue you are having. End of slide 63. Start of slide 64. Slide caption. 12-7 checkpoint. When troubleshooting a motor control circuit, what measuring points should have the higher voltage reading, L1 and L2 or X1 and X2? When troubleshooting a motor control circuit, if the correct voltage is measured between T1 and T2, and not between T1 and T3 or between T2 and T3, what line, L1, L2, or L3, has the problem? End of slide 64. Copyrights originated by the publisher with modifications by Nita Layton and Glenn Graham.